Hello class, welcome to the new topic 2.10, which is solving equations analytically and graphically. We have done some of this before. Basically the new thing is that we're gonna use now the calculator. That's one thing. And the other thing is that I'm gonna teach you a new technique in order to solve equations, exponential equations mostly, which are a little more complex than the ones we have solved before. Okay, but I'm gonna start easy, okay? So I'm going to show you 10 examples of equations. I hope it doesn't take too long. And you can either start working on the workbook on your own or look at these equations for reference. Okay, so it's up to you. You don't have to look at these equations if you know how to solve them in the workbook right away. So let's start. I'm going to start from easiest to hardest. So the first equation we're going to solve is this one. Equation number 1, 2 times 5 raised to the x plus 1 equals 7. So this is what we have. Okay, very simple equation to solve. We have an exponential equation, and basically what I want to do is have the following. I'm going to divide both sides over 2 because the simplest case that I can treat regarding exponential equations is having something like this. Base raised to some expression containing my variable equals another number, which is constant. Why? Because now I can just apply logarithm in both sides of the equation. Logarithm, any base, you can apply logarithm base 5, logarithm base 2, logarithm base 10, whatever. It doesn't make any difference. I'm going to choose for logarithm base 10. Why? For the same reason that I've told you already. Because this is the base that is mostly used in all calculators. Also with the logarithm, with the natural logarithm, okay? So choose either logarithm base 10 or natural logarithm, okay? If possible. Okay, so we have this. And remember that we have one property about logarithms that makes me or allows me to write all of this in this way. Okay. Okay, I'm not going to explain why this is so anymore. You should be able to know by now. And you see that that's the whole thing. Basically applying a logarithm to both sides in order to drop this or to put this down, like so. Okay, now we have this. Next, I'm going to divide both sides of this equation over logarithm of 5. And finally, x will be equal to logarithm of 7 over 2 over logarithm of 5 minus 1. And that's it. You know, if you want, you can make use of this property of logarithms. Remember, the logarithm of a division is equal to the logarithm of the first number minus the logarithm of the second number. And by first and second, I mean numerator and denominator. So it can also look like this. Okay, so that's it. This is my solution. This is my perfect exact solution. There's nothing else to do. If you want to approximate this to decimals, go ahead, but be aware that this is the perfect solution. Okay, there's nothing else to be done. And if you approximate this to decimals, be aware that that's not the real answer. That's just an approximate answer. This is the real answer. So that's the first case. Second equation. What about having this? 6 raised to the 3x minus 1 equals 4 raised to the x minus 2. Now we have my variable in both sides of the equation, or more specifically, one base, which is in this case 6, raised to an expression containing my variable equals another base, raised to an expression that contains my variable. Okay, what do we do? Same thing. I would like to have these two expressions not as exponents, but as factors. Okay, so how can I drop this down? How can I put this down? By applying logarithm in both sides of the equation. Well, logarithm, any logarithm I want. And I'm going to use the most common, which is base 10. So I apply the logarithm in both sides. Then I'm going to have this, right? Sometimes mathematicians either, when you just have a number like so, you can ignore the parentheses. I don't have to do this. Okay, just be aware of that. I want to show you several ways of writing so that you get used to it. This and this mean the same. The parentheses in this case are like irrelevant, so to speak. Okay, next, what can I do now? I'm going to apply the distributive property, 3x times logarithm of 6 minus 1 times logarithm of 6. So I get this, right? Equals, I do the same in here. So next, I'm going to have all my terms with my variable, which is x, on the left side. So it's going to be 3x log of 6 minus x log of 4. And on the other side, I'm going to have all my constants, which is log of 6 minus 2 times log of 4. Next, I can just factorize, okay, because the common factor in these terms are x that multiplies 3 times the log of 6 minus the log of 4 equals to all of this stuff. And finally, I can divide both sides of my equation over this long parenthesis, and I'm done. That's it. One more time. Once you get your x isolated, like alone in one side of the equation, you are completely done. Whether this is simplified or not is none of your business. I mean, you can leave it like this. The whole purpose of the exercise is to isolate x. Have I isolated x? Sure. May this be simplified? Maybe not, but it doesn't matter. If the exercise tells you to simplify as much as possible, go ahead. But if it doesn't, you can just leave it like that, and that's perfect. Okay, there's nothing wrong about this. So this is my final solution and my exact solution. Do not approximate to decimals. Leave it like this. Next example, number 3. We have number E, Euler's number. Remember, it's pronounced Euler. Don't say Euler. It's Euler. Euler. So we have E raised to the 2x plus 1 equals E raised to the 3x minus 1. So now we have a different base. I'm going to erase this because it doesn't look good. Okay, now we have the number E. Is this going to change my method or my, something about my equations? No, it's just a different number, okay? I want you to understand that the number E, even though it certainly has special properties, okay? Very special properties. For all other purposes, it works just as a normal number. You can actually, if I've already told you that this is approximately equal to 2.718, approximately. So you may just think of E as a number close to 3, and that's it, right? So please don't get confused by this number, because from my experience, at least this is what I believed when I was your age or in the first years of college. I got stuck when I was shown this type of equation, because I thought this was something weird. And no, it's just a number, okay? It's just a number. Just like the number 2, number 3, whatever. So I'm going to use the same method that I used before. I have e to some expression equals e to another expression. I'm going to apply the logarithm in both sides, any logarithm. But in this case, it is a good idea to apply the logarithm base e. So I'm going to go like this: logarithm base e of all of this. You're going to know why I chose a e in here in a moment. Equals the logarithm base e of my number on the right. Okay, perfect. Then, due to my properties of logarithms, I can do this. It goes without explanation. You should be able to know by now. Times the logarithm base e of e equals, same thing here, times logarithm base e of my number e. And the reason I chose logarithm base e, it's so that, this is very simple to calculate, right? What is the logarithm base e of e? What is the logarithm base 2 of 2? It's going to be 1, right? Because 2 to the 1 is 2. What's the logarithm base 3 of 3? That's going to be 1, because 3 to the 1 is 3, etc., etc. So it's going to be the same here. This is going to be 1, and this is going to be 1. That's why I chose that specific number. So basically, this is 2x plus 1 equals 3x minus 1. And you can continue with the rest. This is very easy. Okay, next equation. Maybe I'm not gonna complete them all, because it takes a lot of time, and I'm just gonna bore you if I go into much detail. Number 4. Let's do this one. 3/4 raised to the x plus 1 equals 4 to the 2x minus 1. Okay, so what do we do? Same thing. We have some number, some constant, some base raised to an expression containing my variable equals another base raised to an expression containing my variable, which is x. Same idea. I want these two exponents, all of this and all of this, to be put down. And a logarithm helps me do that. The logarithm of my number on the left is equal to the logarithm of my number to the right. And by doing so, I can write this. Okay. Some people, I still see some people making this mistake. Some people write that like so, and this is incorrect, guys. Okay, because it's what the exponent that you're putting down due to the law is all of this number, all of it taken as a whole. So if you have to write the parentheses. Okay, it's all of this that multiplies the logarithm of 3/4. Because if you don't do that, if you just do that, you're telling me that this expression is x plus 1 that multiplies this number. But if I do this, it's all of this number multiplying the logarithm. Okay, it's completely different things. In mathematics, just the absence of one parenthesis makes everything wrong. Okay, there's no room for errors. Okay, same thing. I'm gonna apply the distributive law. So it's x logarithm of 3/4, and then 1 times this, that's going to be plus logarithm of 3/4, and I'm going to do the same on the other side. 2x times the logarithm of 4 minus the logarithm of 4, and the rest is very similar to what we did in the second one. Okay, so I'm going to stop it there. You continue on your own. Number 5. Okay, it's time to show you this new technique, which is very cool. Let's write this. E to the 2x minus 3 equals 2 times e to the x. Okay, so when you encounter something like this, pay attention. I want you to notice the exponents. Okay, we have some base. In this case, it happens to be e. It doesn't make any difference. It could have been 3, it could have been 5, it could have been any other number. It doesn't matter. But if you pay attention to the exponents, which in this case is 2x and in this case is x, they go in descending order of powers. Okay, what I mean is this. Um, you have 2x and then you have x. Okay, it goes in descending powers. It's kind of like when you have a polynomial like this. Look, x to the cube minus 2x to the square plus 3x minus 1. Let's suppose you have this polynomial. If you notice, the exponents go downwards in descending order. You see, 3, x to the 3, x to the 2, x to the 1, and this is obviously x to the 0. You see, so it's very nicely put, like so. Okay, in this case, it's pretty much the same, even though it's hidden. Okay, let me tell you what. First, I'm gonna arrange it so as to have all the terms on the left side. So it's gonna look like this: e to the 2x minus 2 e to the x minus 3 equals 0. So I'm gonna put it like that. And now you must notice that I can write all of this in this way: e to the x to the 2 minus 2 e to the x minus 3 equals 0, right? Because by the laws of exponents, e to the x to the 2 is equal to e to the 2x. Make sure of that. Stop the video and make sure. And that's it, okay? So if you notice, I'm raising this number, e to the x to the second power, and then e to the x to the first power, even though we don't put it. And then you may imagine, and it wouldn't be incorrect, that you have in here e to the x to the 0, right? Because any number raised to the 0 is 1. So we may imagine that. And so we have the polynomial in descending order, so to speak. Well, this is not a polynomial, but we have the expression in descending order of the powers, 2, 1, 0. Okay, so when that happens, what can we do? We can do the following. This is the technique. When you have it like this, when you can put your equation in this way, and you're gonna get it with practice, okay? There are gonna be enough exercises for you to understand what you're supposed to do. Okay, I'm gonna make, need a different color. I'm gonna make a substitution. Okay, which is what in other days I've been telling you is called relabeling. So relabeling, substitution is basically the same thing, okay? I'm gonna decide on my own and due to my own creativity. You know, somebody thought of this idea and it worked. So it's basically, you can think of this as a trick. So this person said, okay, let me write e to the x and let me call it just y. So y is gonna be equal to e to the x. Okay, my equation contains this number e to the x, and basically I'm just gonna call it y. Okay, Why? Because I want to and I can, and that's it. Okay, it's not wrong, so I can do it, and you're gonna see what happens when I do that. Okay, with this substitution, this equation becomes e to the x to the square. What is e to the x? Is y. Therefore, we have y to the square. Can you see? Minus 2 times e to the x. What is e to the x? It's y. Minus 3 equals 0. And look at what you have now. What do you have, guys? Quadratic equation. Very simple to solve. We have seen this before. So, can we factorize in this case? Yes. This is going to be the factorization. I'm going to continue on this side. Okay, I'm going to go quickly straight to the solutions. Y1 will be 3. And y2, my second root, will be minus 1. So these are my roots for this particular equation, okay? But this is not the equation that for this particular equation. This is not the equation that I'm trying to solve really. I'm trying to solve this equation, guys. This one. Now, all that remains to be done is go back to my relabeling, okay? If my first root for y is 3, and y is equal to e to the x, then I go back to the e to the x form, okay? So I'm gonna write e to the x equals 3, or e to the x equals minus 1. You see what I did? Maybe, you know, I'm gonna erase these subindexes in order to differentiate the roots from one another, so I don't confuse you, okay? I'm gonna erase these two subindexes, okay? What are my roots for this equation? Y equals 3 and y equals minus 1. But what is y? Y is equal to e to the x. So I'm gonna go back to that expression. You see, y is equal to e to the x, then y equals 3 is the same as e to the x equals 3, and this is the same as this. And now finally, we isolate the x. We have e to the x equals 3. Now we just have to go to the logarithmic form of this expression, because this is an exponential expression. If e to the x equals 3, that's because the logarithm base e of 3 is equal to x. Have we isolated x? Sure, because it's alone on one side of the equation. And it's basically, I mean, if we write it in this way, it looks better. Okay, I'm done. X is equal to the logarithm base e of 3, which is commonly written in this way. X equals natural logarithm of 3. These two things, guys, this and this mean exactly the same thing. Exactly. So get used to it. So this is my solution. Logarithm base e of 3, which is the same as natural logarithm of 3. Perfect. Next, what about the other? What about this other root? Okay, let's go there. So we have e to the x equals minus 1. Okay, now there's a problem with this, guys. Okay, there's a problem with this. Why? Because you don't have to lose sight of your exponential function. I told you before that, you know, if you consult your workbook, you can look at the graph of this function of e to the x, and it's gonna look something like this, if you remember, more or less. This is the graph of e to the x. Okay, this is your axis for the x variable, and that's it. So my question is this: is there any number x along this line? Any number x? And remember that this line goes in this fashion, but it never crosses the x-axis. Is there any number along the x-axis for which this function, or e to the x, is minus 1? No. Why not? Because the graph never crosses towards the negative side of the x-axis, right? Of the Cartesian plane. There is no number such that when you raise e to that number, you will get a negative number. Okay, so it's not possible. So what happens here? Nothing. Okay, which we just say that this doesn't provide this other root doesn't provide a solution to the equation that we had to solve. Okay, only this one makes sense in the context that we're talking about. Okay, if you actually input this in your calculator, and I like you to do it in a moment when I tell you how to solve the equations with your calculator, you're gonna get an error. Okay, like there's no answer for this. Okay, so that's the only solution, and we're done. Um, takes a lot of time. Okay, next, number 6, right? What about this one? E to the 2x plus 2 e to the x plus 1 equals 0. Same idea. It has the same shape as the last one, so I'm gonna make the relabeling. I'm gonna say y, let y be equal to e to the x, because if I do that, now my equation, which can be written in this way also, now my equation can be written like y to the square plus 2y plus 1 equals 0. Make sure, please. And then this is equal to y plus 1 to the square equals 0. Then we have this. Gonna go a little faster. And then we have y equals minus 1. So this is the root I have for y. But what is y? Y is equal to e to the x. So e to the x equals minus 1. So what's going to happen in here? The same thing. There is no number x such that my base e, or any other positive base, such that any base raised to that number will be negative. The reason I showed you already, because your function for e to the x is always above the x-axis. Okay, so e to the x will, this number will always be positive. Okay, because for example, look at this, at this number, e raised to this particular number of x will give you a positive number. You see, e raised to this particular number of x will give you this positive number. This other number of x, e raised to that number will give you this number. So it's all positive numbers. You never get numbers in here. So this equation has no solution, and therefore we conclude that this equation has no solutions whatsoever. Okay, remember, not all equations have solutions. That's not a necessity. It's not a guarantee. Equation number 7 is going to be e to the 3x plus 3e to the 2x equals 3 times 2e to the x plus 6. Okay, so this is the equation. This equation, guys, is worked in the same way as number 5 and number 6, even though it's a little more complex because we have now like the highest degree is 3 in this case. Okay, 3x, not 2x. Okay, so we're gonna go one more degree in complexity. So let's first simplify this expression a little more. gonna multiply all of this. Then I'm gonna have all my terms on the left side. And now if you notice, it looks very similar to number 5 and number 6. Okay, basically number 5 and number 6 were something like this. Can you see? Go back to them and you're gonna notice that they look like this. We have only one more term of highest order than these three, but that doesn't really make much of a difficulty. So let's see why. Let's continue. Okay, I'm gonna restate my equation in this way: e to the x to the 3 plus 3 times e to the x to the 2 minus 6 e to the x minus 18 equals 0. Let's relabel. I'm gonna call this number e to the x, I'm gonna call it y. Same thing as before. And by doing so, my equation becomes, or is transformed, so to speak, to this other equation. You see? So now we have a polynomial equation of degree 3. And in some cases, even though we have only seen so far how to solve equations, quadratic equations like this, and not cubic equations, because those ones are harder. For some cases, for some simple cases like the ones I'm gonna put in the workbook, you can actually work out some sort of factorization or some sort of easy manipulation of the equation that's gonna give you the result rather easy. In the general case though, in the general case, a cubic equation is much harder to solve than a quadratic equation. But I'm talking specifically in the general case. So let's see. I'm gonna apply here something called factorization by grouping. And what that means is the following. I'm gonna, for example, I'm gonna select this term and this term and this term and this term, and I'm gonna rearrange like so: y to the cube minus y to the 6 plus 3y to the square minus 18 equals 0. This with the idea that maybe I can factor these two terms and then these other two, like so. Look, what is the factor in here? What is the common factor between these two terms? It's gonna be the y, right? So you're gonna get y that multiplies y to the square minus 6. Can you see? And the common factor between these two terms is the number 3. So I'm gonna call it this plus 3 that multiplies y to the square minus 6 equals 0. You see? So basically I'm factorizing first these two plus the factorization of these other two. This is known as a partial factorization. This is not yet a complete factorization, as you can see, because we have a plus in there. But happily, we can factorize again, because now between this term and this term, we have a new common term, which is y squared minus 6. So I'm going to factor that term. I'm sorry, that factor, y squared minus 6, that multiplies y plus 3 here equals 0. And I'm done with the factorization. Now this is a complete factorization. It's something times something. One factor times another factor equals 0. You see? And now you can apply the common idea that the product of two numbers being equal to 0 leads you to say that the first number has to be equal to 0, or the second number has to be equal to 0, right? And finally we have this, y squared equals 6, and that means that y equals plus minus the square root of 6, or y equals minus 3. So these are my roots for the equation in y, And now we have to go back to the relabeling thing, okay? Because my original variable is x. If you stop right here, you're incorrect, because I mean the original equation is not even about y, it's about x. So if you stop right here, you're wrong. So I'm gonna go in blue. Okay, what is y? Y is equal to e to the x. So I'm gonna go like this. I'm gonna use this, and I'm gonna say e to the x equals plus minus the square root of 6. And the same here. E to the x equals minus 3. This implies that I have two solutions in here, which could be e equals to the square root of 6, or e equals to minus the square root of 6. Okay, so we have this possibility, and this possibility. Which ones could not lead me to any answer? This one and this one. Why? Because e to the x can never be negative. Okay, e to the x equals minus 3, wrong. That's impossible. There is no number x that can give you this. E to the x equals the negative of the square root of 6, wrong. There is no such number x. So I might as well forget about these two things. And the only root that's going to be useful is this one. Now we're not done. You have to isolate x, right? So I'm going to erase this because we don't need it anymore. You can ignore it completely. And finally, I go like this. If e to the x is equal to the square root of 6, that's equivalent to saying that the logarithm base e of the square root of 6 is equal to x. Or in other words, x equals the natural logarithm of the square root of 6. And that's perfectly written. Do not approximate this as a decimal, okay? This is the perfect solution. Get used to seeing numbers like this. There's nothing wrong about this, nothing weird. The weird thing is to say that this, and you calculate this thing and you go like x equals 1 point blah blah blah. That is incorrect, okay?